Hey everybody, welcome back to HPC Tech Shorts, where every week we take you to the water cooler here in HPC Engineering at AWS, and we talk to the engineers and the other nerds that are making the cloud a great place to do HPC. This week, I'm joined by Pete Mendygral. Did I get that right? Did I say it right?
Close enough.
Close enough. Anyway, Pete is a principal engineer in our performance engineering team in HPC Engineering, and day to day is working on all of the things that plumb up underneath an instance that make the application software run really fast. We've been doing a series of talks over recent weeks with folks about Elastic Fabric Adapter. And one of the topics that always comes up in, when we're talking about EFA is, of course, how we compare to on-premises equipment and how we compare to supercomputers elsewhere. And of course, one of the least favorite things of mine to do is to get into discussions with customers or with other people about MPI ping pong, because it's almost industry have allowed some marketing folks to reduce absolutely every aspect of whether a cluster is usable or buildable or runnable for code. We've reduced everything down to like this one metric, which kind of actually is a bit of a synthetic and artificial number. So I have a bit of a pet peeve about that. And Pete, you've got a really interesting view on all of this, because you were one of the co-authors of the GPCnet benchmark, which studied how applications behave under network stress when things got busy, which is actually kind of like a more practical kind of approach to it. So that's why I was hoping we could talk about application performance today.
Yeah, I was just going to pick it up from there. That the work on GPCnet was sort of motivated by a similar kind of feeling about a lack of complexity, a lack of sophistication in the way we try to characterize HPC networks when it comes to actually measuring them. Certainly in the design phases of networks and things like that, they have really complex simulators and understand all of these things. But how do you take an implementation of a network and actually measure its capability and ultimately be able to make some comparisons and trade-offs about how you design a network in terms of topologies, what kind of equipment you use. Really, the state of the art is that, or at least the common case is that MPI benchmarks are used, and they're absolutely useful for trying to understand how an MPI library behaves and performs. So things like collectives and all the different features of MPI, but they're not so good at assessing how well a network behaves per se, like how well a network is going to be able to absorb really sophisticated communication patterns that may have a lot of demand on them, because ultimately the network's a shared resource, and we, in looking at it from the perspective of just like a single MPI benchmark, that you learn something from that, but it's not the whole picture.
Right, and I think you mentioned in a talk you've done elsewhere that I was researching earlier, that using something like MPI ping pong to assess the characteristic is kind of like it's like testing your commute to work by driving through the streets at 4 a.m. when there's nobody else there. It's not going to give you an accurate depiction of what your commute's likely to be the next morning or the next part of the day at 9 a.m. in rush hour when everybody else is trying to go there too. And it's not a bad comparison, actually.
Yeah, well, I can't claim credit for the analogy. I absolutely agree with it. That it's useful to understand how quick you can do something in ideal situations, but yeah. The users in this case really want to understand how their applications are going to perform in a day-to-day basis.
Yeah, and that kind of goes to an interesting After Brian Barrett, our principal engineer for EFA, and I did a talk the other week where we're discussing a lot of the aspects of SRD, and talking about SRD and how it actually reacts to the network inside AWS, and one of the things that came out of that was that actually performance is probably more tied or more driven by P99 tail latency. And I got a couple of messages in my DMs on Twitter asking to dig into what P99 tail latency means, because a lot of folks didn't quite understand what that meant and really wanted us to go there. So can we talk about that for a few minutes?
Yeah, and I think the way I'd like to do it, if we can, let's talk about how GPCnet measures it. There are different approaches, and I think if we can at least talk about how it implements it, and that's a good place for discussion. Yeah, so I think it's useful to understand how GPCnet measures P99 tail latency, and in fact, it measures more than just that. One of the challenges in designing a benchmark of any kind is with regards to a network is what kind of communication patterns are you gonna be testing. MPI ping pong is really just two processes on two nodes talking to each other, and one of the things that you guys discussed with Brian was, there's a lot of paths on the network, and when you're trying to understand how the network's going to behave when it's busy, which means a lot of those paths are carrying traffic, you need something that actually can sort of probe as many paths as possible on the network. Because if you're only probing, a couple of them, the rest of the network might be really, really busy, and you're not measuring that. But a real application would, right? If they were running on lots of nodes doing sophisticated things. So what you want to do is have some kind of a canary, is what we call that, a canary communication pattern that can probe and feel out all of the performance along lots of different paths. And what we settled on was using natural and random rings, and they have different properties. The reason we use rings at all, and the way we implement them is to make sure that we're not measuring on-node communication whatsoever, because that's irrelevant to the question of how well a network behaves. And so that's carefully designed to make sure we're only doing off-node traffic. Yep. And what we do is we start with a natural ring, which is just every rank in the ring has a neighbor to its left and right, and it will do some kind of exchange with it. Could be a small message or a large message. And if you have multiple ranks per node, each rank on a node is in its own unique ring with other ranks that are at the same offset on a different node. And so you'll have as many rings running as you do processes per node. And so if you keep a natural ring, that means it's always the node to the left, the node to the right, and that's it. So it's a very, very kind of trivial pattern. All you need to do then to make it very sophisticated is randomize which neighbors you talk to the left and right. And that's what the random ring does. And if you do that, you get something where the way we like to describe it is in terms of connectivity between the processes. And just like an MPI application might have a particular rank talking to lots of different ranks, but maybe not all of them. There's some amount of connectivity in the application. Like, in an extreme case, every rank's talking to every other rank. And in a very trivial case, maybe they're only talking to two other ranks. So a random ring is somewhere in between. So you get a very sophisticated communication pattern with, perhaps some levels of incast and some places where it's, behaving really nicely. So now we've got something where we can move data on the network in a very sophisticated way and feel out the performance along lots of different paths. So that's kind of our basis where we're going to start measuring something like tail latency out of.
Right. Okay, and so that necessarily means you're going to start seeing, between any two particular pairs, Q pairs, you're going to see tons of different latency profiles across that entire cluster. As the cluster gets bigger, you're going to get even more, right?
Exactly. And so what we do then is, for measuring something like the tail latency, each of any given rank is going to talk to a random rank on the left and on the right, and just do basically the same thing MPI ping pong does. Just fire off a bunch of, do a bunch of send receives of very small messages and measure the latency of those. And so but the big difference being we're doing it, with a really complex pattern, and we're doing it at scale. So we're feeling out lots of different paths. And so every one of those exchanges, those small message exchanges, we measure the performance, and you then just make a histogram. How many counts of exchanges were at latency, X, Y, or Z, and you bin that up, and you get a nice distribution. And I think we've got a picture of one that we can talk about.
Here we are. Here, it's this top left one, right?
Yeah, that would be a good one.
Yep. Let me just futz around with the thing. There we go. I think everybody can see that. Yep.
Yeah. So if we focus on the upper panels, I think just to start, the topmost one is a isolated, quiet network, nothing else running on it, and we're running different numbers of processes per node. And so, like a normal MPI application might, in this particular instance, I think these nodes had 32 cores per node. It would run with 32. The term is P port because it has to do with how many network ports. But let's just pretend there's one network port for right now. And so you get some very complicated pattern there. You see at something like the peak of the pattern on the top left is maybe 1 or 2 microseconds, and that's what your MPI ping pong would measure, right?
Yep.
But you see there's a big long tail off to the right, which is values at increasingly larger latency, all the way out to almost out to a millisecond, right?
Yeah, that's actually fascinating. There's orders of magnitude difference here.
Yep, and this is an isolated, quiet network. There's nothing else happening, just these little 8-byte messages shooting around on this particular network. And so what is the P99? The P99 is the latency value at which you sort of keep counting up how many samples there are to the left of you on the diagram until you get to 99% of the samples are at that latency or better. So, or lower latency. That's your P99 tail. And, why is that important? MPI applications, or, most HPC applications implement some kind of algorithm to solve some kind of physics, right? And they're decomposing that problem up into some fashion that allows them to do it across multiple processes. But there has to be some communication. Could be in the case of like CFD, boundary values. And in other cases, they may have to perform some kind of collective operations depending on the algorithm. And all of those, because there's explicit communication, may have to wait for that data to get to another process, right? Yeah. And especially in the cases of collective operations, like a hard synchronization or a reduction, you're actually going to be waiting for the last process to check in. And in fact, the last bit of data that last process checked in. And there's different ways of softening an application's sensitivity to that. They can use non-blocking communication, etc. But at some point, there's some minimal latency that has to be provided by the system, or that application is going to be just hung up, stuck, waiting for that data. And that's why that tail latency is so important.
It really just comes back to that aspect of MPI, what you were just describing there, which is, in MPI codes, particularly tightly coupled codes, everything, an MPI application is only as fast as the slowest node, right? And so, uniformity of execution speeds is pretty key, right? So, okay, so the P99 tail latency, that all makes sense now, and I think hopefully folks will get a grip on that. And I think what's interesting there is the orders of magnitude difference. That is astoundingly big. That is that's a gulf. I know a lot of folks who've done the MPI ping pong tests in the past, and they've typically done them with a couple of boxes back to back, even without a switch.
Yeah, and the important thing is that top panel there was, like I mentioned, an isolated network. The one right below it, so the second from the top, is now where we're loading up the network with additional traffic and seeing what happens to that latency distribution when you load up the network. And look at the transformation you get.
Wow.
And let's focus on that green line in particular. So on the top one, you see that it's got some extra power at maybe 10 microseconds, and that's probably jumping over a couple of switches and such. But now when you load up the network, there's a lot more power in that distribution, all the way out to 100 microseconds. And that's what's happening, is you're shifting all of those samples from that, ping pong latency measurement all the way out to something much worse. And if your application load on your system actually is that really demanding on the network, and again, it's a shared resource across users, that's what'll happen. And your latency sensitive applications or your collective sensitive applications will slow down because of that.
Right. And so, of course, it just gets, I guess, hang on, where's my, sorry, I'm having mice issues here. And of course, it just gets even worse. The larger you get, the more.
Right.
And this really just means that on a, which one of these do you think is going to be, quote unquote, a normal, like a normal practical environment?
Yeah, I would say these are the two extremes, right? So the isolated case is essentially an empty network aside from the latency packets we're shooting around. The loaded case, that's using GPCnet's congestors, which is there's sort of two different types of traffic GPCnet generates. There's their canaries and our congestors. And the congestors were designed to be pretty extreme. We're trying to push the network quite hard. And so that's going to be what happens on a larger system, this lower panel. You see now we've got latency values shooting out to almost 10 milliseconds, out to 10 milliseconds. That's pretty extreme. Does it happen in real life? Occasionally, probably yes. It really depends on the workload, the characteristics of the network at hand. But it can happen. But probably, practical experience is somewhere in between the two, and it's really workload specific. And so the idea was we want to show the two ends of the spectrum.
Right, and somewhere in the middle is going to be the classical cases where somebody else on the cluster, because typically HPC clusters are not just one user; they're shared. It's a shared environment, and so. You can't predict what somebody else is going to do on the shared infrastructure. The network is a shared bit of infrastructure, if nothing else, right?
Exactly. Right.
So all of this is good, and I think we should be we got to be cognizant of the fact that we're not here to talk today. Here's AWS's numbers when we ran the GPCnet benchmark, and I think we should actually, we have to be, for full disclosure, we have to talk about why, right?
Absolutely. So let me give just a quick overview of how GPCnets run, and that I think will then lead us to why, where we're at with numbers on AWS. So GPCnet was designed under the assumption, and actually under it almost requires the fact that you can run it on nearly the entire network, because if you're trying to push a network, can you push it with just a fraction of the nodes injecting data onto the network? No, you can't. You need something that can really fill up all the buffers on the network and push it hard, and that requires using most of the system. And that's been a criticism, and a very valid criticism, of the benchmark, and something we still have to keep working on. But so we're able to run the benchmark on on-prem systems because you can get during service time or something like that, the whole machine to run these tests on and understand what's going on. You can't do that in the cloud. We have customers running stuff constantly, and we're not going to push them aside just out of. Yeah.
Right. They might notice if we took US East 1 down for a weekend so that we could run GPCnet.
Exactly.
In fact, the New York Times will report it for us, and so will CNN and everybody else.
So that's not really an option. So what we have been investigating is just using the canaries, just those sensitive patterns, what kind of variation we see over time in performance. And, we haven't completed those studies yet. Preliminary data shows it's actually quite low. There's not a lot of variation. But more work to be done there yet to be certain that's the result.
But the lack of variation is probably something that we should reasonably expect, because the way that SRD behaves, the way that the scalable reliable datagram that lives underneath EFA behaves, I mean, its objective is to find, the objective of the protocol is to find as many paths as possible and spray the packets out across multiple paths. We're never at the mercy of any one particular path being congested at any one time. It's not like we have to spray a bunch of packets out. Oh, look, it's congested. We need to react to that and, redirect a bunch of packets that got lost because of the congestion. Where, it's actually a proper parallelized algorithm for spraying packets out all at once. We should expect that as we go to larger cohorts of nodes, with more paths necessarily, we probably should be able to have a fairly flat experience. To
I think that's scale. I think that's a reasonable expectation. It'll be interesting to see if in fact that's how it pans out.
Yeah. So what about how about with other? I mean, we're going to almost certainly see some variation across other clusters. Every cluster is unique. Every cluster is designed to solve a different problem, right?
Yeah, that's right. And there's different approaches to dealing with the issues of a loaded and congested network, right? There's different solutions. There's different vendors with different products and different approaches to dealing with this issue. And AWS has its own approach to how to prevent really long tail latencies and such. We have SRD, and then we also have just the way that the network, the topology that's been chosen and how it's configured. So yeah, with GPCnet, within the GPCnet paper, we did study what we called the congestion impact, which is essentially how much worse did the tail latency get when you loaded up the network with our congestors. And we just looked at that across a bunch of different implementations of both InfiniBand and Cray networks. It's difficult to compare any two systems because, as you mentioned, they're designed for perhaps very different reasons the way they are. Choices were made about whether or not the network was tapered for a variety of reasons. Topologies were chosen for a variety of different reasons. And so it's important to understand that context, but it's still, what is the impact of a really aggressive load on the network going to be on real applications is a valid question, and it's one that we're trying to answer with GPCnet.
So Pete, what about congestion management? Because SRD's got its own approach to congestion management.
Yeah, there's more than one valid approach to dealing with the effects of congestion and designing a network to be able to deal with it. There's explicit congestion control. Some of the capability in SRD is like that. There's hardware implementations of that. Both other vendors have different degrees of sophistication around explicit congestion control. And the other approach is just having a really large network, having lots and lots of buffers on your network such that it's essentially impossible for any meaningfully any reasonable aggressive application that's really pumping a lot of data on the network to overwhelm it. And I think that last thing is how I'd kind of characterize the AWS network, is it's a very, very large network with lots and lots of different paths on it, and it's really difficult for even a group of users to overwhelm it, and for significant effects of congestion to show up.
Yeah, and look, you're right. We designed it with all of the vendors who design their fabrics and their networks to do it with a different goal in mind. Our goal in mind, as Brian explained the other week, was we wanted to be able to leverage the infrastructure we've got, very large Ethernet infrastructure. We want to be able to keep it all running, and we can't shut it down for a weekend to refactor it, and we can't. And it's always expanding, and we can't ever turn stuff off. We had a lot of different requirements and an extreme growth requirement too. So we had a lot of different requirements that pushed us to come up with EFA. It may not work brilliantly in somebody else's network, but it works really, really well in ours. And as we saw before, it gives us really great application performance. So, Pete, thank you for coming today. Appreciate it.
Thank you.
This is a good discussion, and I think if we can ever figure out how to, if we ever have a weekend where we can turn off a whole region, we'll get you to run GPCnet and see how it goes.
That would be very fun.
Well, it would be fun for you, but not for some other people who may be wanting to use that thing. Anyway, thanks very much. I really appreciate it. If you've got ideas about what you'd like us to cover on a future tech short, if you've got some thoughts about different topics you'd like us to dig into or people you'd like us to speak to, find us on Twitter, DM us. Our DMs are open. We'd be more than happy to add that to the suggestion box, and we'll see what we can do. Anyway, for now, thanks very much, Pete. Thanks for coming in. Have a great weekend.
Thank you. You too.